Hola, buenas. Ya estamos en los últimos momentos de la conferencia, ya. Em, Antes de dar la introducción para nuestra última keynote luego de estos 3 días de PyCon en Chile, quería avisarles que la charla a continuación estará en inglés. Hicimos lo posible para poder tener una traducción, no pudimos por cosas de tiempo, lo pedimos de antemano disculpas, pero a pesar de que en mi charla les comenté que los problemas del inglés, tenemos confianza de que por lo menos van a poder seguir esta charla. Es una charla bastante interesante, em, con lo que espero que no sea ningún problema para todas las personas que nos están viendo. Entonces ahora voy a cambiar a inglés. Okay. So, thank you everyone for joining now. I'm really, really happy, personally happy to have the following keynote. I had the luck to meet Luciano, I think in the PyCon Germany at some point. Maybe he don't remember, maybe he does. I will ask him later on. But yeah, I mean, it was really nice because I do remember when I was studying that I found this fluent Python book around, and then I noticed like, oh, Luciano, maybe this person is from South America, and then yes, I was lucky to have that. Well, and before introducing Luciano and welcoming him to the stage, I just wanted to share a few things about him. I mean, first of all, of course, he's a fellow of the Python Software Foundation for all the things that he has been doing in the Python community for such a long time. Currently, he is the main consultant in I think, in TalkWorks. Also, he is a co-founder of Garoa, so the first hackerspace in Brazil. And if you are maybe closer to what the global Python community and the Brazilian Python communities are doing, you might have seen it in many, many other events. So without further ado, I just want to welcome Luciano on stage. Hey, Luciano.
Hello, Christian. Yes, I remember meeting you. Yes.
Cool.
I didn't expect to see you here today, but yeah,
Yeah.
awesome. Yeah, my so I think I'm honored to be invited to speak at PyCon Chile. I apologize for not being comfortable presenting in Spanish because I did study a little bit of Spanish, but it was years ago. I haven't practiced. I need to solve this problem. Anyway, hopefully
It's
next time you
fine.
invite me, I will speak in Spanish. But for now, I think one of the obligations of not the obligation. Okay, I think it's nice when you're invited to be a keynote speaker to try and broaden the minds of the people, right?
Right.
And that's what I'm going to try to do with this talk, which is kind of a little bit of a radical talk because it's kind of a condensing in 45 minutes of a tutorial that I've presented at PyCon Europe and Python Brazil in 3 hours.
Okay, well, fair enough. It's a good
No,
exercise.
yes. Well, anyway, I'm gonna. Of course, it's gonna be different from the tutorial, but it's the subject is the same. So let me
Perfect.
get started. Did I? I'm sorry. Maybe you asked me
You need to
something.
just
That
share the screen, I think, at the
yes.
slides, and we will be ready to
Yeah.
go.
Yeah. I'm gonna do that and open the slides here, and then present, share screen. Yes. Okay.
I can see your screen now, and I can see the presentation as well. So,
Awesome.
Luciano, I will not take any more from your time. I'm really, really happy to see you here and to join in this beautiful event. That it's the second year that we have a PyCon in Chile, so it's really an honor to have you. And
Awesome.
with that,
Thank
please.
you so much. All right. So the talk is called "A Beautiful Python" or "The Art of the Interpreter," and so Alan Kay, the leader of the team who created. Let me close my window here. The leader of the team who created Smalltalk, right, and invented object-oriented programming, the term object-oriented programming, once was in an interview, and he said, he answered to the interviewer commented, so Lisp was carefully defined in terms of Lisp. And then he answered, yes, that was the big revelation to me when I was in graduate school, when I finally understood that the half page of code on the bottom of page 13 of the Lisp 1.5 manual was Lisp in itself. These were Maxwell's equations of software. This is the whole world of programming in a few lines that I can put my hand over. Okay, so Maxwell's equations are just 4 equations that unified many fields in physics, right? And so what I'm going to talk about is I'm going to give a little bit of context why I find this topic interesting. First, I learned that the best starting point to understand how programming languages work is to study interpreters and not compilers. Compilers are interesting as well, but interpreters are simpler, so you can more quickly get to the semantics of the language, right? And Lisp was the first language focused on symbolic processing instead of numeric computation. And interpreters and compilers are symbolic programs, right? It's possible to implement a Lisp interpreter in 2 pages of Lisp. And that's how John McCarthy, the man who created Lisp, presented it to the world. So this is a Lisp interpreter in 2 pages actually 1 page, 66 lines, is a page of code, right? There's some missing definitions here, but the beautiful pattern that I mentioned in the title appears here. The beautiful pattern is this function called eval, okay? So in this talk, we're going to study a simple Lisp interpreter written in Python, and you will see the following concepts applied in practice. Why program translators use an AST, which is an abstract syntax tree to process code. And I'm talking about program translators because this applies to interpreters and compilers. Compilers also usually have this internal representation of the program as an abstract syntax tree, which we're going to see how it works. And then we're going to see how pattern matching can be applied to AST processing. So pattern matching is a new feature in Python. Of course, we could do everything that I'm going to show you here before using ifs and ifs, but with pattern matching is easier and safer. And then we're going to see how a closure is implemented and used in an interpreter. Because this is interesting to me because I had read a lot of blog posts about closures when I was studying JavaScript 20 years ago. And I was very confused about the definitions. And I really only understood what a closure is when I saw the code for a little interpreter, similar to what I'm going to show you. And the concepts that we're going to talk about apply to most languages, compiled or interpreted, okay? So this is another small Lisp interpreter, but this one is written in Python, which has the advantage of being easier to read for me and probably for you as well, right? This is 132 lines of code, so it's 2 pages of code. And it was written by Peter Norvig, who is a famous computer science professor at Stanford, also the author of a very important textbook in artificial intelligence. Now, the rest of the talk, we are going to spend really looking at code, which is interesting. And the best way to look at code, in my opinion, is to go to to GitHub, right? And browse it so that you can do it as well. So I just clicked on that link, and now you can see. So the link was, again, let me just show you, right? So github.com, if you want to follow on your own computer, github.com/fluentpython is the organization that I created to host the examples in my book. And Lisp is one of the examples of the book, but I don't talk so much about it as I will in this talk. In the book, I only use it to basically to show an interesting example of pattern matching. So this is the first page of the Lisp project inside Fluent Python. And there's so the original Lisp interpreter that in Python that I've shown to you is this one here. That's the one that I basically took screenshots and made the slide showing. See, 132 lines of code. And you see here the val function with a series of if-elifs and so on. We are going to get to that. And this one doesn't have type hints and so on. But it's a beautiful piece of code that I recommend studying. And that's what I've been doing when I have time for a while. And I created this other one called MyList. Okay. So, and what I did was basically MyList is built on top of Norvig's Lisp, all right? But then I added other functions here in this MyList package that uses a lot of things from list.py. Okay. So this first version, I wanted to change as little as possible I wanted to change as little as possible the code from Peter Norvig, and then I built more features on top of it in MyList 2, and then MyList 3 is one that I just refactored just for you guys, just to show, just to present this talk. Okay, so what I did basically was I split the code, which the original code from Peter Norvig is a single file. I separated. So here, for instance, is only the parsing functions, and then I also wrote tests. Peter Norvig doesn't have a lot of tests in his code, but I wrote more tests. And what else? Yeah. MyList 3 is this version here. I have this program. This is the main program, and it actually works as a command line application. So I'm going to show you how it works. So for instance, I can do, for instance, if I call just MyList, and it gives me a prompt, right, where I can write an expression. So this is the syntax of Lisp is Polish notation, right, which is the operator in front and then the arguments in parentheses, right? Usually we are more comfortable with infix notation for expressions, but this expression that I typed shows one advantage of Polish notation is that the operators don't need to be all binary operators. They can take many arguments. Like for instance, if I want to sum, I can put 0 arguments and then it gives me 0. But I can also, I can also put 2 or how many arguments I like. Okay. If I open an expression here, then the prompt changes to those 3 lines because it knows that I'm not done. So we can do this and then, all right. So basically this is the little interactive interpreter, and I hit .q to quit. And it also works with a program, like for instance, let me show you a little program. So code examples, there's a fact SCM, for example. This is a little factorial program, right? So this is just a simple factorial program that uses this display command, which is like print to show the result, okay? And the factorial is named, this is interesting, the factorial function is named exclamation, because you can use exclamation as an identifier, okay? So here I am showing the factorial of x, but x is not defined anywhere here. So I invented this simple command line integration, which is like this. If I go my list, examples, fact, then I get this warning that x was not defined, but I can define it as an option in the command line. So if I do the same command and I say x equals 10, then that's the factorial. All right, so the mylist script takes command line arguments written like in this format, identifier equals value, and passes them as arguments, injects them into the global environment of the program. Basically, that's what's happening. Okay, so that's just to play around. If you want to play around, afterwards if you download the code, you can play with this mylist.py program. But I'm going to show you another thing, which is another piece of content that is in this repository. So in this repository, I have this workshops folder, and the ThoughtWorks and the EuroPython workshops are in English, and the Python Brazil workshops are in Portuguese. Okay, so for example, if I go to the EuroPython repository, what I have here is a Jupyter notebook. And if you run it, if you click on this button, Launch Binder, which I'm going to do right now, something amazing is happening, right? I don't know if all of you know about Binder, but Binder is a place where you can basically construct a special URL of a public repository on GitHub, and it will check out the code and or the Jupyter notebook and run it in the cloud. So I don't need to have anything installed on my machine. The problem is that this only runs using Python 3.7. That's the only version of Python that's available. Last time I checked in the Binder platform. But anyway, here you can see the content of the tutorial that I present, and the tutorial has exercises, right, where the participants, and you can just follow along this later if you're interested. Just do as I did, click on that button, then you're going to have this notebook running live, and you can read it, and I explain a lot of things. So one of the things that I wanted to show you here was precisely let me remove some things here so that we can have more space. Okay, so the syntax of Lisp is a little bit weird with all those parentheses, but if you indent it, then it becomes easy to read. And here I've done a little program in in Lisp and also in Python. And the way I did it in Python is not the way I would usually do. I wouldn't use recursion to compute the GCD. GCD is the greater common denominator, right? But I wouldn't use recursion to do that in Python. But I don't need to implement mod in Python because that's already the percent operator. But I wanted to do it in this way because I wanted you to be able to look at this code and see how similar they are. If you just abstract a little bit, you can see two function definitions and a top-level command to run, display, and call the GCD function. Like we have here, two function definitions, and then the print command. The call to GCD is here. The call to GCD is here, right? You see the expressions are a little bit weird because of the syntax of having the operators, the prefix operators, right? But the one advantage of this is that it's super easy to write an interpreter for this. And that's why, and so the reasons why John McCarthy was able to present Lisp to the world, and I have a reference, in the end, I have a reference to his paper, but the way he was able to present Lisp to the world in an academic paper by writing a little Lisp interpreter in Lisp. In 1959, he did that for three reasons. First, because he was super smart. Second, because Lisp was suitable to the task, because it was designed for symbolic manipulation. The basic data structure of Lisp is a linked list, which is pretty flexible. And the third reason is that Lisp itself is easy to implement. At least a naive implementation that is not super efficient is easy to implement, right? So, and that's why it's also possible to write a simple Lisp in Python. Anyway, so this here will present in this tutorial the different parts of the program as a single program, which is like the way that Norvig's LispPy works. But I want to show you the way that I organize the program so that you can understand the main parts. But the first part is the parser. So in my version, in my Lisp tree, I have the parser as a separate module, right? So that's easier for you to see the tests and everything. But this is basically it, and I'm not going to explain how the parser works because the most important part that I want to show you in this short time that we have is the evaluator, okay? But basically the parser, what it does is it takes, it follows three rules. The syntax of Lisp is very simple. So a token that looks like a number is parsed as a float or int, right? So what is a token? It's an atomic piece of code. Like, for instance, a number, a complete number, not a single digit, right? A complete number is one token. An identifier, a series of characters that follow the rules for what is a valid identifier, is another token, right? An identifier. And we have the tokens, super important tokens, open parentheses, close parentheses, right? But anyway, so a token that looks like a number is parsed as a number. Anything else that is not open or close parentheses is parsed as a symbol, okay? And a symbol in this simple Lisp of Norvig's interpreter is a string to be used as an identifier, right? If we wanted to support strings as a native data type, so that we could manipulate, strings, then arbitrary strings, be able to split strings, do those kinds of string operations, then of course those rules would be more complicated because we would have to be able to quote strings and so on. But in this simple interpreter, strings are only used to represent symbols, which are identifiers, okay? But the rules are very flexible in Lisp. So plus, set exclamation point, and make dash counter are valid identifiers. Okay. So this is the second rule. The third rule is expressions that appear inside parentheses are recursively parsed as lists containing atoms, and the atoms are the floats, the ints, and the symbols, right? Or nested lists that may contain atoms and more nested lists. Okay, so this is parsed. Just to demonstrate, I'm going to run this. Wait, I need to run everything up to this point. Yeah, run. Okay, so if I parse this, the result is a number, see? If I parse this, the result is a symbol. If I parse this, the result is a list of symbols and nested lists with more symbols, and there's even a number in there. So does that make sense? I am not able to look at the, I'm going to try. Let me see if I can look at the Discord. I don't know if people are interacting on Discord. If they are, I don't know where. Yeah, I'm going to give up because I'm kind of lost in the screens. Anyway, so, and so this here, although it does not look like a tree, is a representation that in the Python world we call an abstract syntax tree. In many, in modern language processing, these are called abstract syntax trees. So the idea is the abstract syntax tree is an in-memory data structure that represents the code in a way that is easy to parse, not to parse, it's already parsed, but in a way that's easy to process, for further processing. For instance, in an interpreter to actually execute, right? So, like I said, this does not look like a tree, but if you organize it like this, then you can see it as a tree, right? So this is the outer list. The outer list contains 3 elements: the symbol define, the symbol double, and this other list here, right? This other list contains also 3 parts: the symbol lambda and 2 lists. The second list here contains only one symbol, the symbol n, and the other list contains the symbol star, asterisk, the symbol n, and the integer 2. Okay, so this is the AST. So what the parser does basically is to convert source code into this representation. Okay, so this is the first lesson. The idea that for you to process the program, you need to have a more convenient representation than the source code. And a very convenient representation for the source code in Python, for instance, is a list of lists and symbols and numbers, right? Okay, so, and then there's a bunch of exercises here that we are not going to do, but I'm now going to go back to the to GitHub to show you the parser. So this is the parser module, right? I did a little enhancement compared to Norvik's version, which I accept as instead of just parentheses, you can also use arbitrarily the way you want. Also, brackets, square brackets, and curly braces, right? So this makes code a little bit easier to read. But anyway, there's a. I'm not going to explain this code. This here is the inverse function of parse. it takes an AST and returns a string that it corresponds to a source code that would generate that tree. Okay, so this is basically the parser. And another thing that I did that you won't find in Norvig's code, let me increase the font size here, is I added type hints. So it's easy to see that parse takes the source code as a string and returns an expression, right? And so what is an expression? If you look here, you will see that expressions come from my types. And my types is another module here where I define a bunch of types like for instance, expression is a type alias that represents the union of atom and list. So an expression is either an atom or a list. An atom is either an int, a float, or a symbol. Actually, I could use the number here, but I didn't. Anyway, the number is either an int or a float, right? And a symbol is just a type alias for a string. We want to be able to call strings symbols in the program, okay? And there's a bunch of exceptions. This is basically it in this module. Some type definitions and the exceptions that I use in other parts of the program. So now let's go to the main part. So my list. So my list, what it does is the main program. If there are commands, if there is only one argument, which is the program name, then it calls the REPL, which is the read, eval, print, loop, that interactive prompt that I demonstrated. Otherwise, it's going to call this function called run file. It's going to open and read the file and run it. Okay, so run file. So this is a lot of code. That's just for usability. Okay, this is not essential code. It's code that I added to be, to play around with the interpreter more. So run file calls run, and run calls run line, and run lines. What it does is it calls for each line. This read from tokens reads expressions, parenthesized expressions, and then I evaluate each expression. Okay, so evaluate is the key here. And now let's go to evaluate. This is the beautiful pattern. These are the Maxwell equations. The core idea is here. So evaluator. Okay, so evaluator. There's a class called the procedure. We're going to talk about it a little bit later. And then we have evaluate. So evaluate is a function that takes an expression and an environment. And it can return anything, the result of the program. We don't know what it is, okay? But it can, so the expression is either an atom or a parenthesized expression, right? And the environment, what's the environment? So the environment is a namespace that contains the definitions. Like, for instance, to be able to say, when I say, for instance, let me take the example here, right? So when I say, for this program to work, for instance, the factorial SCM to work, let's take a look at it. For the factorial to work, define has to be defined somewhere. This is what we are defining right now, which is the name of the function is the exclamation point. This operator, less than or equal, has to be defined. If has to be defined somewhere. The star operator, multiplication, the minus operator has to be defined. So those definitions that are built in, like we say in Python, have to come from somewhere. And in addition, the program, like for instance, when you say define, you're actually you're adding an item to the namespace, right? You're saying we're going to have a new function called exclamation point, right? And this is the body of the function, right? So the environment is modified by the program. Now let's take a look at the environment, because what I'm saying here is evaluate takes an environment. In the main, we saw that I passed the global environment. And how are these things defined? So there is a module called environment, right? There's environment, actually. And it defines a little class that derives from chain map, because there's an additional method that I need that chain map doesn't provide. But chain map is something from the Python standard library that is a way to represent nested namespaces. A namespace can be represented as a dictionary, but it can also be nested in another one. So you look in the first one, and then if not, you go to the next item in the chain. That's why it's called the chain map. So it's a way to combine several dictionaries in a chain, so that the search starts on the first dictionary and goes through the dictionaries until it finds or doesn't find a certain key, right? And the core environment, which is the built-ins in this program, is basically an environment, which is basically a dictionary, with definitions like this. So what is the definition of minus? We can use the definition of the sub-function of the operator module in Python, which is the minus operator defined as a function, right? This is part of the import operator here. Import operator is OP, right? So we have a lot of operators like this, simple things. The max function is the max function in Python, works exactly the same. The min, there's different things, but there's also, for instance, the quotient, which is the division that returns an integer, right? It's the operation is called floor div in Python, and we write it as two slashes, right? But it's defined as a function called floor div, and so on, right? So this is basically a dictionary where these are some basic definitions for a little Lisp, and there is also this operation here starts the environment by adding all the definitions from the math module. So all the functions like sine, cosine, and so on are defined in the math module are also available in our little interpreter, right? So this function core env builds this core environment and returns it, right? There are some functions that are defined below here, like for instance, display. Display, this is the definition of display. And there's a variadic comparison. I invented this function here this is because you can compare several variables at once, like equal A, B, C, D, E, to see if they are all equal, and so on. I created this version here that is variadic comparison is a shortcut to avoid repetition. But anyway, I want to explain that. The main thing is the environment is a dictionary, but also some operations change this dictionary. So let's go to the main to the evaluate evaluator module. So this is it, folks. I'm gonna reduce the font size a little bit so that we can make evaluate fit in a single screen, right? So this is basically it. So as you can see, these are the rules of Lisp expressed in an extremely readable way in Python using the match case construct of Python 3.10, right? So what we're saying is, what is the value of the expression that I get? If the expression is an integer or a float, just return it. We don't need to compute anything. If the expression is a symbol, I will look it up in the environment, which is a dictionary, right? If there's a key error, then we return undefined symbol, right? So when we look up a symbol, we look it up in the environment. Now define. Define has two versions. One is to define simple variables like this. Define x 10. So this case will match if the first part of the expression is the keyword define, and the second part of the expression is a symbol, and the third part, so the third part we are going to assume is an expression. So then we evaluate the expression. So this is a recursive call to the function here. And then the result of this, so we evaluate the expression in the environment, having access to whatever else is also already defined. And then we put it in the environment, right? The other variation is a shortcut to define functions with names without using lambda. So it's define the name of the function, a series of parameters, and a body, which is a series of expressions. So this is what the match is saying here. Okay, so in this case, I'm going to increase the font size a little bit. So in this case, we call the constructor of the procedure call, right? So what does this do? The procedure is created with three parameters, right? The constructor takes a list of symbols, which is the name of the formal parameters, a list of expressions, which is the body of the function, and the environment where it is created. This is what makes it a closure, folks. A function in Lisp is a closure because it captures the environment where it is defined, so that when you call it later, it can refer to functions, to symbols that are in this environment that may not be available at the call site. This is the fundamental idea of a function, of a closure, right? The if is cool, the way to implement it. It has four parts: the if keyword, a test, a consequence, and an alternative. So the first thing we do is we evaluate the tests. If it's true, then we evaluate the consequence. Otherwise, we evaluate the alternative. And this is very interesting because this explains why if cannot be implemented as a function. Because if was a function, imagine this situation here where the test is if the user is authorized, make the withdrawal. Otherwise, report to the auditors. Okay? In a function call, think about this, folks. In a function call, when you say the sum of A, B, C, the values of A, B, and C are computed before the function is called. The arguments are calculated, are computed, are evaluated before the function is applied to the arguments. Does that make sense? That's how pretty much every language works. Of course, there are lazy evaluation, but that's another story. Okay, but basically, most of the languages that we use work like this. The arguments are evaluated before the function is called. If the arguments are evaluated, if was a function, then these three expressions would be evaluated before, which means if the test was false, either way, actually, it doesn't matter what the result of the test is, because you would evaluate the test, and then regardless of the test, you would evaluate the consequence, which means the withdrawal would be made, and then the alternative, which means the auditors would be notified. So if was a function, it wouldn't work because the three arguments would be evaluated before. So this is a key idea of this, of the reason why we have keywords in languages like if, defined, quote, and so on, because the keywords affect the way that things are evaluated. And this is what we are seeing here, right? We don't evaluate consequence or alternative always. We only evaluate a consequence if the test is true, otherwise we evaluate the alternative. In the case of quote, which is a very interesting reserved word in Lisp, we don't evaluate anything. Quote is a way to transform source code in data. When you do quote and then write an expression, you get that expression as a list of symbols and integers and numbers and lists so that you can process it, right? Anyway, so this is the main idea that I wanted to show you guys. This idea that, if you have time, go read my explanation of how the interpreter works. And play around. This is fascinating stuff. You get a lot more insights with a few hours of studying than you would get with several weeks of a compiler course at the university. I guarantee. Okay, so now let's go back to my slides because my time is over, and I would like to see if we can have questions. Let me. Okay, so this is the code that I wanted to show. And the last slide basically are the references that I recommend, okay? The Art of the Interpreter is a classic text where a little interpreter is implemented in different ways, showing different advantages and disadvantages. The Roots of Lisp is a blog post by Paul Graham that talks about the history of Lisp and the original paper where John McCarthy described it. A Conversation with Alan Kay is where I got the quote of the Maxwell equations of software. This other blog post here also talks about that. And this is the repository that I've just shown you. Okay? All right. So this is what I wanted to share with you. I hope I was able to raise your curiosity to dive into this subject. It's, like I said, much more profitable than taking a compiler course at the university. You can do that as well, but after playing with interpreters, it's going to be much easier.
Exactly. Thank you very much, Luciano. It was really an enlightening talk. I didn't have the pleasure yet to participate in the workshop, so it was certainly a nice summary. So,
yeah, my timer. Okay. Yeah.
Oh, okay. I thought there was some fire alarm or something. Okay,
No.
Cool. No, I mean, it was really nice. I also enjoy this approach of trying to improve or increase your kind of knowledge, understanding of things by doing this kind of useful, in this case, interpreter for Lisp. Out of curiosity, if you were not able to choose Lisp, is there any other functional language, for example, that you would like to maybe attempt to write an interpreter for as an exercise?
Well, so yeah, there's a lot of books that follow this approach of playing with Lisp-like languages because of the fact that the syntax is so simple that you don't
simple.
spend a lot of time with the syntax. Now, there's a thing that I don't like the syntax very much. Okay, to be honest, you get used to it, but I don't like the syntax of all of those parentheses. But one thing that is interesting to talk about is that the Lispers defend the syntax by saying it's easier to do macros. But there's other languages like Rust and Elixir, which I think are two very interesting modern languages that have macros and that don't have that simple syntax. So I'm interested in learning more about. I've been studying Elixir, and Rust is as my next language to study.
Yeah, no, Elixir sounds really good as an
Yeah.
alternative. So we have well, not on topic because it's your keynote, but you had an interesting question when you started to the talk. Is there any, since we are in a PyCon Chile, of course, is there any Spanish translation of your book, The Fluent
No,
Python? Because
unfortunately,
I was sharing there a tweet that I remember from 2 years ago that I think it is your shelf maybe with the many languages that you have there, and Spanish was not there. So
yes. So yeah, this is complicated because the problem is that O'Reilly retains the right for the translations. So they have
right,
to, but they have to convince a publisher to translate it, right?
I see.
No, this is literally what happens. So if you know of good, and the book has been very successful. Okay, it's because I think it filled a niche when it was released. There wasn't a lot of intermediary or advanced books that were up
Yeah,
to
you
date
were,
at
at
the
least
time.
that was my argument when I first met your book
Yeah.
many years ago, is that I needed like a more advanced book,
Yes.
that
Exactly.
filled.
And so we need to as a community, if you can recommend a publisher that you like that does good translations,
Hmm.
we should give them put them in touch with O'Reilly and see if they would do the translation.
Yeah, certainly, certainly.
Yeah.
So if anyone here listen or maybe watching the recording knows one,
Yeah.
drop a comment.
Yeah.
We do have another question that by Camilo, that he was asking if there's any minimum version of Python to try the code that you just prepare for the talk. You're using
So,
type hints, I guess. So I
yeah,
guess that.
that's a very good question. So I spent the last minutes showing the case the match case statement, and that's only available in 3.10. But
Okay.
the same interpreter, or a very similar one, in the tutorial that I presented, the workshop when I opened the Jupyter Notebook, that one is written in 3.7, right? So it's I had to use 3.7 there because it was the latest version supported at Binder,
Hmm.
and I
And
wanted to,
okay.
yeah.
And there was a follow-up version of Camilo, is that if that version that you prepare for the workshop, it's complete, or you are thinking of any additional functionality, just as
Well,
a
yeah,
cherry on top, maybe.
yes, I am actually. So if you look at the code in my list two implements a very interesting feature which Python doesn't have, but Scheme, which is a famous dialect of Lisp, has, which is tail call optimization. That gives you the ability of doing recursive calls efficiently without using the stack. So this is a feature that I put in my list too. But then when I did the whole refactoring, you will see a significant refactoring from my list 2 to my list 3. I haven't gotten that far in my list 3. I'm probably going to do that in my list 4 again.
For
So
the
I'm
PyCon
working.
next year.
Yes, and there's also another interpreter by Norvi called lispy.py instead of list.py. Lispy.py has string support, has macro support, and has tail call optimizations, but it's
Oh,
like 3 times as long as the original Lispy, and it's much harder to understand. But I'm working my way into having all that functionality in my list as well, but done in a way that is more familiar for Python programmers who like to see, tests and type hints and so on.
okay. And out of curiosity, since you mentioned this, like improvements that I was curious if you had the chance already to play around with Python 3.11, because at least for the version that you show us, it's a really good argument to explain to people that the match case, for example, is much more powerful than a switch case, because it's something
Yes.
that
Yes.
there has been some
Yeah.
comments around. But I'm
Yes.
curious if you have tried 3.11 or maybe some of the features there.
No, not yet. And
Okay.
no, yeah.
Because there's something that you mentioned that this adaptation of improvement that you said before, it's something that I guess that could be quite similar. There's one of the features that called quickening. Maybe you can see one of the core developers keynotes about it. Somehow they are adding into Python now a way of detecting when you have, like, for example, a simple sum of two integers. So they have an optimized virtual machine
Oh,
symbol
okay.
there to do that
Yeah.
in a
Uh-huh.
more smart way. But of course, I mean,
Yeah.
there's some caveats and everything that would be
Yeah. Well,
interesting.
so this is this project of playing with these little Lisps or little Lisp variants is an old thing for me. And one thing that I want to get to is actually to get to a compiler. And probably the first compiler that I would write would be a
Mhm.
compiler to transform Lisp into Python bytecode.
Oh, that was my follow-up question, because I mean,
Yes,
since you
yes,
have all this essence of
exactly,
Lisp there, I mean, you are
exactly.
one point away
Yes,
of doing binary
yes,
add or whatever.
yes. And then after doing that, it would not be hard probably to do another one using LLVM to generate, actual machine code.
Yeah.
But
Oof.
yeah, I've
LLVM are different words.
yes, I've played a little bit with all of these things, but I haven't done that with Lisp yet. So I've explored.
Okay.
Yeah,
That is a good idea for certain.
yeah.
Luciano, thank you very much.
Thank
It
you
was
so
really,
much
really
for
nice
inviting
talk.
me. I hope to be in Chile next time, and I hope to speak Spanish with you guys.
Likewise, and hopefully we can see each other again in one of these
Yeah.
conference in the world.
Yes.
Anything. It was really nice to meet you. So
Bye
yeah,
bye.
thank you
Yeah.
very much, and
Bye
see you
bye.
around,
Thank
Luciano.
you so much. Bye
Bye.
bye.